How you doing? I'm Mr. Rose, and for this next example of Gauss's law, we're going to do things a little differently. I'm going to introduce a little bit of different terminology that you should be familiar with, and it's going to be a different kind of problem. For this problem, let me outline for you. We're going to have a sphere, which we've done before, except this time I'm going to charge the outside of the sphere. I'm going to put a negative charge on that sphere, and I'm actually going to put a charge inside the sphere as well. And then we're going to examine two different places. We're going to examine one place inside of that sphere, one place outside of that sphere. Okay, so here I have the outline of what I just described. I have got a sphere that's charged -16 E, and that E is an elementary charge. So instead of just giving the net charge, often we'll have it written as this with elementary charges. So this is -16 times 1.6 times 10 to the -19th. My sphere had a radius of 10 meters. There was a charge inside that I've labeled small q of 5 elementary charges. That's at the center of the sphere. And we're looking at the electric field at two different points, point P1 and point P2. Now, drawing a sphere isn't specifically helpful. So over here, I drew a cross section of the sphere where I have this ring to represent my outer shell. That would represent the entire sphere. Point P1, which I know is inside my radius, a radius of 0.1, P1 is 0.06, point P2 outside of the radius. So I'm going to look at, or outside of the sphere rather, I'm going to look at these two different points in two different steps, and things that we need to remember when we're doing this, we're going to apply Gauss's law, which means since I'm dealing with a sphere, I'm going to apply some kind of symmetry. I'm going to ID that we're going to use spherical symmetry. Meaning, I'm going to draw a Gaussian surface. First, I'm going to start with just point P1 and closing in that. So I'm going to apply a Gaussian surface at point P1. So I'm going to apply a Gaussian surface at point P1, or really just around point P1, not really at point P1. From there, what we're going to do is we're going to find the electric field. I'm going to find the electric field using Gauss's law from only small q at P1. And we're only going to do small q because we need to also remember that Gauss's law only deals with a net electric flux of some enclosed charge, meaning the external charge has no effect. So the net flux of the enclosed charge, I can ignore big Q for this very first part. So what we're going to do is I'm going to place Q right there. Just make sure that's on our screen. Perfect. I'm going to place Q right there. I'm going to imagine some Gaussian surface. I'm going to put point P right on that Gaussian surface. That's point P1. So now this is my enclosed charge. And I know I have an electric flux. That's a positive charge. So I've got an electric flux going in that direction. And remember, it's actually, sorry. Remember, it's actually a shell, a sphere. So I'm going to put a little dA because I have vector dA that's coming out of that as well. Make sure we're still. Now I'm going to apply Gauss's law. And we remember that we have a surface integral of E dot dA is equal to my charge, I should label that, Q, my charge enclosed, divided by epsilon naught. I could rewrite all my givens. All the givens are up there. Hopefully you've written them down. Just the Q. I will put Q1 just so I have it right here. I know that's 5 elementary charges. And I know point P1, which is now equal to my radius, is 0.06 meters. There we go. Just trying to get it all. 0.06 meters. So I'm going to apply my Gauss's law to that Gaussian surface. Here I know that E and dA are in the same direction, so that's actually parallel to each other, so that's 0. So if I really wanted to, I could write out E times dA times cosine of 0, but I know that they're parallel, so it's a maximum. I'm not going to worry about that. I'm going to pull out my electric field out of the integral. So my electric field, E, comes out. That's just the antiderivative of dA is equal to Q enclosed over epsilon naught, my permittivity constant. From there, I know that the area of dA, the antiderivative of dA is summing up all those areas of my spherical shell. So I know that the antiderivative of dA is just A is equal to Q enclosed over 4 pi, jumping the gun there, over epsilon naught, where A is equal to 4 pi r squared. So now we should start to recognize some things coming together, right? Area is the area of my sphere. So now I'm going to have, move that up so we can see, I'm going to say E times 4 pi r squared equals my Q enclosed over epsilon naught. I'm going to divide both sides, and now that should be something that I recognize. That means my electric field at point P is equal to 1 over 4 pi epsilon naught times Q enclosed over, r squared epsilon naught. I just got into the habit of writing out what we know. If I switch that, Q over 4 pi r squared epsilon naught, that's something we've seen before. That is my general solution. I plug in my equation. I would have, 5 times 1.6 times 10 to the negative 19th divided by 4 pi times a radius of 0.06 squared times epsilon naught, or epsilon 0, and epsilon naught is 8.85 times 10 to the negative 12th. Just give me 1 second on the calculator. I'm actually going to edit this part out, and we'd get an electric field of 1.99 times 10 to the negative 6th, 2 times 10 to the, an electric field equal to 2.0 times 10 to the negative 6 newtons per coulomb. That is the electric field at point P1 inside of that shell. All right, so now for the second point, point 2, I'm going to redraw just an easier sketch than this, but we're looking for now the electric field due to two different charges. So before we got to ignore Q because it was outside of our Gaussian surface. I didn't care about it as it was floating out here. Now point P2 encompasses both, and we haven't done something like that yet. So I'm going to just quickly draw. We've got Q1 there. And now not as good as my first drawing. I've got Q2 there, and I'm looking at point P2 here. Again, that point P1 that was inside, I don't care about. It was just some arbitrary point. Now I'm going to draw my Gaussian surface. Just add some color to this. I'm going to draw my Gaussian surface to find out what it is at P2. Now, I'm enclosing all of that charge, so I'm looking at point P2. So we need to deal with two different things. We need to have our Gaussian surface, like I said, just repetitive, enclose both of those things. But what we need to do is we need to not confuse the actual sphere. I don't want to confuse the actual sphere with my imaginary Gaussian surface. That's a mistake that I often see people make. So what is my Q? My Q now, or my Q enclosed, is equal to what we labeled big Q plus small q. Well, big Q, if you recall from the front of the page, was negative 16 elementary charges, plus a small q, which was 5 elementary charges. So my Q enclosed now is just negative 11e. I don't really care what the whole thing looks like, it's just negative 11e. If I were to draw what it looks like at point P2, here's my point, P2. Well, again, I've got my dA vector in that direction, but now I've got an electric field going in that direction because my electric field is negative. So we know electric field is the direction of a positive test charge would act. Since my charge is negative, my electric field is going the opposite direction. So we just derived this on the previous page. I don't have to go through it again. Of Q enclosed over 4 pi epsilon naught r squared, where now my Q enclosed is negative 11e. So I guess I could throw out a negative on top of that if I wanted to. So my electric field at point P2 would be negative 11 times 1.6 times 10 to the negative 19th divided by 4 pi epsilon naught r squared. I want to put in our constants there, divided by 4 times 8.85 times 10 to the negative 12th times r of 0.12 meters. Don't forget to square that. And when we throw all of that into the calculator, we get an electric field equal to negative 1.098 actually. So 1.10 negative times 10 to the negative 6th newtons per coulomb. That's all I have for us today. Please feel free to like, comment, or subscribe, ask any questions, and you'll see me next time.